This is our agenda. So we'll start by looking at the motivation for cross-ECU timing analysis and typical use cases. Then we will pick one particular and I guess also quite common use case, measuring an event chain across two ECUs which communicate with each other. And since we will actually do it here in this webinar, I will of course describe our demo setup. Basically two Infineon AURIX TC399XE devices communicating with each other via a CAN bus. Next I will, at least to some extent, explain how a time synchronization between the iSystem blue boxes connected to the AURIX devices actually works. And last but not least, we will demonstrate the whole thing here. So I will run a synchronized trace, and based on this trace recording, we will do an event chain analysis. And as said, we will do that in two possible ways. First, by also using vector TA inspection, and also by using some advanced features of the iSystem trace analyzer. So first, let's look at our motivation, why we want to do this. And just to make things clear, I'm using the term ECU, meaning electronic control unit. We're not talking about multi-core within one chip, but really about multiple microcontrollers or SoCs. So we're looking at systems where two microcontrollers or SoC are coupled together, maybe due to safety, redundancy reasons, or simply because they communicate with each other. One type of use case here is safety-related systems. Systems which try to achieve a very high safety level by applying redundancy and synchronicity. So for example, two ECUs controlling the same safety critical functions, maybe for example steering motor. And the controlled function requires that the ECUs operate with a certain degree of synchronicity. The timing analysis use case here would be to measure and verify the synchronicity and maybe also test how the system behaves in case of an error. The other type of use case is more about communication, and the timing of this communication is in some way critical for the correct functionality. So the interesting time aspects here are properties like communication delays, end-to-end response times, and event chains. And this is exactly the later case, the event chain analysis across two ECUs, we want to take a closer look at in this webinar. This slide depicts such an event chain, basically a communication between two automotive ECUs. Let's call it here master ECU and slave ECU. The event chain gets initiated on the master ECU by some sort of stimulus within a certain software component, so some sort of runnable entity. Then the signal propagates through the RTE and the communication stack, gets transmitted via a network, for example CAN bus, and on a receiving ECU, the signal goes up the COM stack again until it reaches some sort of consumer. And it may trigger some sort of response, which may be acknowledged back to the initiator. This is pretty much the event chain we want to analyze today. Here you can see the concrete realization of this CAN communication event chain. This is actually a screenshot taken from the vector TA inspection tool. On the top, you see some OS tasks and ISRs running on the master ECU. In the middle, you have task ISRs and runnables of the slave ECU. And on the bottom, you see the transmission of the CAN frames over the bus. So the event chain obviously goes like this. At point 1, the master initiates the event chain by a request to send out a signal via the CAN bus in the CAN frame master request. In stage 2, this CAN frame gets transmitted via the bus. In stage 3, the CAN frame transmission completes, and after some delay, a CAN receive interrupt service routine executes on the slave ECU. This ISR in stage 4 spawns an OS task, here the task RT event task. The runnable modify echo is the actual consumer of the data signal. This runnable confirms the receipt of the data. In our case here, the acknowledge is done by means of an implicit write access. So sending out the acknowledge frame is actually initiated after completion of the modify echo runnable by calling the COM send signal basic software function. This is basically our stage 5. And finally, the CAN frame slave acknowledge is transmitted on the bus with quite a delay, as the CAN frame was taken already by some other frame. Okay, so this is basically our scenario. Okay, now I guess we pretty much understand what we're trying to do, what our use case is. Now we take a look at the tool setup needed to actually measure such a distributed event chain. So we have our two ECUs communicating with each other via a CAN bus, the master ECU M and the slave ECU S. In our demo, both ECUs are equipped with an Infineon AURIX TC399XE microcontroller, and the E in the end of the product name says that this is a so-called emulation device. So this device implements hardware trace. For tracing the software activity within the AURIX device, we connected to iSystem trace tools consisting of the winIDEA IDE, an IC5700 BlueBox, and an iSystem active probe to establish a high-speed trace connection to the target. Now, for performing a synchronized trace on both targets, the two blue boxes need to be connected by some sort of a synchronization interface. This is why the blue boxes are equipped with a so-called sync hub and also a so-called F-bridge between them. Such a tool setup now allows a synchronized tracing of two targets. And I want to emphasize that the tool setup is not based on any AURIX-specific synchronization features. This is a generic approach, which can be applied on various different other devices as well. And in our demo for this webinar, we will also add some more measurement equipment. We will also record the CAN bus traffic with our CAN-LIN add-on module. And we will monitor an AURIX trigger output pin, the TG4 pin, with our analog digital I/O module. Both are hooked up to the IC5700 connected to the slave ECU. This slide shows the demo setup I actually have here in front of me on my desk. On the back side, we have two IC5700 blue boxes with the sync hubs installed on their top side. The two sync hubs are connected via an F-bridge. So these two pieces here are actually the ends of the same F-bridge cable. The little black boxes are the active probes, establishing the high-speed trace interface between the blue box and the target. On the left-hand side, the master ECU, we have the DAP interface, using also as a trace streaming interface running at 160 MHz. And on the right-hand side, the slave ECU, we use an Aurora gigabit trace probe running at 2.5 gigabits per second. And as said, the ECUs communicate via CAN bus. The add-on modules here are actually hidden here in front underneath the PCBs. Here the CAN-LIN trace box and here the IDEO box. Both of these boxes are hooked up with the blue box here of the slave ECU. Yeah, so this is the hardware I'm actually using here. Next, I want to give a bit more information about the principles about synchronizing the trace recordings of two individual microcontrollers or SoCs. The challenge here is that both trace recordings need to use the same common time base, or in other words, we need to have kind of one common time base counter which runs off this common time base. So this timestamping is obviously an important aspect here, and therefore we need to distinguish two scenarios here. The first, and also the more straightforward scenario, is the case where the trace messages coming from the target are timestamped off-chip, meaning they get a timestamp when they get captured by the trace tool, meaning by the blue boxes. In this case, we only, in quotes, need to synchronize the timestamp counters of our blue boxes. So the timestamps of our IC5000 blue boxes for recording the software activities, and optionally also the timestamp of, for instance, a CAN-LIN box for recording the CAN bus transactions. Such an approach can typically be applied to rather low-end or maybe mid-range microcontrollers, for example, controllers using a parallel trace port. But yeah, unfortunately, life isn't always that easy. On higher-end microcontrollers and SoCs, this off-chip timestamping of trace messages cannot be used. This is because such processors typically implement some sort of internal buffering of the trace data, and therefore the propagation delay of the trace message from the point in time they get generated by a processor core until they reach the recording tool is not constant. So the trace data generated by the chip already carries this time information, which is derived from on-chip timestamp counters. So in this case, not only the blue boxes need to be synchronized, need to synchronize the timestamp counters, but also they need to be synchronized to the on-chip timestamps of the target processors. And such concepts need to be applied, for instance, with AURIX TRICO devices and also with some higher-end ARM Cortex-based SoCs. And as mentioned, here in our demo, we use an AURIX TC399XE device, which uses on-chip timestamping. Okay, now we go a bit more into details about how we can actually run such a synchronized trace. So we start again with our two target ECUs and add the individual debug and trace tooling connected to them. As a next step, we add a possibility to synchronously debug both targets. So some connections of the F-bridge allow for synchronously run and stop both ECUs. Then for the synchronized trace, the F-bridge also allows sharing a common trace clock, and it allows, through a common trace trigger, to synchronously start the trace recording in the blue boxes. The whole setup actually also requires a Python script acting as the overall control instance for both winIDEA workspaces. And as said, we have the possibility to measure CAN communication and system level signals. Now, these CAN and signal traces can not only be synchronized into the trace of the software running on the targets, they may also be used as a common trace trigger to start the overall trace recording on certain events, such as a toggling device pin or a certain CAN frame. Now, before we can actually run a trace, we have to make a few preparations on the target. One prerequisite for synchronized tracing is, for instance, that the target outputs a continuous stream of trace data. For microcontrollers with parallel trace port, where we use external timestamping, this is a given anyways. But for an AURIX device, for example, which we use in our demo here, this is actually relevant. And it means that we cannot use the approach of storing the trace data in the on-chip emulation memory. Instead, we need to stream out the data either via an HBT trace interface, or we need to operate the DAP interface of the AURIX in a streaming mode. And at iSystem, we call this the upload while sampling mode. On microcontrollers or SoCs which use on-chip timestamping, in addition to the trace streaming, you also need to get access to the on-chip timestamp counter. And in which way this can be accomplished depends on the individual processor. Some devices, it may even not be possible at all. Okay, so we're almost there. As I mentioned earlier, we need a Python script as an overall controlling instance. What the script actually does is a bit more than just starting the trace. This is why I want to discuss this here briefly. Here at the beginning of the script, we first create some objects to control the IDE and trace recording of both the master and the slave winIDEA workspaces. The real interesting part happens here. What the service call does, it reads out the current timestamp counter value of the blue box connected to the master ECU. This timestamp is used later on during the profile analysis as a common time zero point. The next slide will illustrate this a bit better. So for setting this time zero reference point, we write back this timestamp into the blue box of both master and slave. This set option time offset activation forces both blue boxes that all timestamps obtained during the following trace session are referenced against the same time zero timestamp value. Okay, so the illustration comes actually one slide further. This slide first shows the remaining part of the script, where we simply start the trace generation on both ECUs. And finally, we inject a trace trigger which synchronously starts the trace recording in both blue boxes. In this case, we basically inject the trace trigger via the API of the master winIDEA instance. And the trigger is passed on with minimal hardware delay via F-bridge connection between the sync hubs of the blue boxes. So here, we inject the trace trigger via the API. Alternatively, we could also generate the trigger manually in the GUI, so by a mouse click. And we could also have the CAN-LIN box assert the trigger, for example, when a certain CAN frame is transmitted on the bus. Or maybe the ADIO box, for example, when it detects that some board level signal gets asserted. And one more word regarding this trace start commands here. As said, these commands start the trace generation in the target. This means these commands write the currently selected trace analyzer configuration into the on-chip trace logic, meaning the registers of the AURIX device. And especially on an AURIX device, this may be quite a number of registers, and this is also why these operations actually consume quite a considerable amount of time. Okay, so now this is actually the slide where the script operations are illustrated. Here at this time, we read out this time zero reference timestamp value for the master BlueBox, meaning this point in time will be our common time zero in the profile timelines of both the master and the slave ECU. And you see, this causes kind of an odd offset until the first real trace data appear on the timeline, but it is actually needed. If both traces would operate independently, each profiler would simply choose the time when the first trace data is received as its own time zero point. But here, the first trace data of both traces appears at different times, so both would have different time zero points. This would simply not work. Therefore, we have simply chosen that this common time zero topic is best handled by a Python script. Then, after configuring the on-chip trace logic of both devices, the actual trace data output starts here at point 2 in the slave ECU and at point 3 here in the master ECU. And finally, at point 4, we inject the common trace trigger to start the recording in the blue boxes. Wait a second, you said trace recording starts with the trigger. How come there is trace data already before that? This is due to the way this recorder triggering works. And this is what I want to briefly explain during the next slide. So what I'm talking about here is the trace buffer, the 1 GB big trace buffer in the IC 5700. And yes, for those of you who are a bit familiar with the AURIX device, yeah, the AURIX device also has a trace buffer inside, the emulation memory, EMEM. But in our case here, this EMEM is not really used, only a small portion of it, since we stream out the data via AGBT or via the DAP interface. So I'm talking about the trace buffer of the BlueBox recorder. And this trace buffer can be separated in two parts, the pre-trigger FIFO and the post-trigger buffer. The pre-trigger FIFO, as the name implies, is used before we receive a trigger signal, and it operates in a FIFO fashion. So a circular buffer always overwriting the oldest data. And even if we set the trigger position to begin here in the recorder properties, we will still allocate a reasonable buffer, roughly like 16 megabytes, for this trigger FIFO. And this is where the trace data before the trigger injection actually comes from. After the occurrence of the trigger, we simply keep all the received trace data, buffer it, and at the same time we try to stream the data up to the PC. And usually with a USB 3 connection to the PC, all data can actually be streamed kind of endlessly to the PC. So this is how the synchronized tracing works. We haven't looked into the event analysis yet, but I think now it is time for a demonstration on real hardware in winIDEA. Here you can see the two winIDEA workspaces. On the left-hand side, we have the master ECU workspace, and on the right, we have the slave ECU. Here under the menu Hardware Options FNet, we see what kind of iSystem hardware tool configuration is used. On the master ECU, we have just a DAP active probe and the sync hub connected to the IC 5700 base unit. On the slave ECU, besides the AGBT active probe, here we also have the CAN-LIN add-on module and also the ADIO AOM. Another important part of the configuration here is the workspace synchronization. This is also done here in the hardware options, then under BlueBox Sync. So here on the master side, we define that this workspace, this winIDEA instance, is the sync master, and its internal timestamp is part of the overall timestamp synchronization scheme. And we need to define which other winIDEA workspace acts as the slave. If we take a look in the same dialog on the slave side, we see that this workspace is declared as the sync slave, and its time is also part of the synchronization. Okay, so with these settings, the two winIDEA workspaces are now coupled for synchronized trace, but also for synchronized debug. This is also indicated by this little star here, this little star symbol here next to the status indicator. I won't go into details about sync debug here, but here, for instance, if I push the run button on the slave side, also the master ECU starts running. So both targets now are running, and I can verify this, for instance, by doing a test trace recording first on each target separately. First here on the master. So we trace the OS tasks and one runnable, actually a basic software main function. And also here on the slave, we trace OS tasks, some functions which we have declared as runnables, but here also the CAN bus and the signal measured by the ADIO box. But these two trace recordings are not synchronized in any way. For running a really synchronized trace, we need, as I said, the help of our Python script. And this is what you see here. As I said, the important operation here is the reading of the BlueBox time from the master BlueBox and then writing it back to both BlueBoxes as the common time zero reference. Then it starts trace on both master and slave, and finally here the injection of the trace trigger. And speaking about the trace trigger, for a synchronized trace, we need to configure the recorders to actually wait for a trigger for the trace recording. So we need to do this on both trace recorders here in the analyzer configuration on the hardware recorder properties. Start recording not immediately, but in this case on trigger. And here on the master, we also, since we use a DUB active probe, we need to select upload while sampling mode. Here on a slave ECU, use AGBT, which is inherently a streaming interface, but we also set this to on trigger. This is pretty much all the special configuration that is needed for synchronized trace. The rest of the trace configuration is rather AUTOSAR specific and specific to the tricore. So let's run the Python script here with tools run script. Okay, so here we have the trace recordings with our common time zero point. This marker here in red is the common recording trigger injected via the script, via the API. But now, how can I convince you that these traces are actually synchronized? So let's pick one characteristic point here in the slave, which basically is our event chain. We see some delay time after the master request frame, a CAN receive interrupt gets triggered. And now in the master side, we should find approximately at the same time a CAN transmit interrupt. So, 'Okay, so here we have the trace recordings with our common time zero point. This marker here in red is the common recording trigger injected via the script. And now in the master side, we should find approximately at the same time a CAN transmit interrupt. This is basically here. But of course, we have different software running on both ECUs, so the interrupt response time is of course not exactly the same. But you see, if you compare these two numbers here, we are not like completely off. And later on, I will actually show you a much better evidence for the exact synchronization. So, as you can see here in the profiler settings, we also include network in the profiler analysis. And this is what you see down here. Here we have all the detected CAN frames, and they are listed, displayed both as frames, meaning the actual transmission of the frame over the bus here from start of frame until the end of frame, and also the signals mapped into each frame can also be visualized. I'm mentioning this here because for some event chains it may be needed to look at the signal value transmitted on the bus and maybe link this to a data value within the runnable which sends out this CAN frame. So by doing this, we can guarantee that we actually measure the correct event chain. But in our case here, we just look at the frame timing. So with regards to our event chain here on the slave, we can measure the events starting with the transmission of the master request frame, the CAN ISR, the RTE task spawned by the ISR, and the runnables within the task, and finally also the slave acknowledged frame on the bus. But the actual start point of our event chain is traced by the winIDEA master instance. So the overall event chain is still distributed over two ECUs and therefore also here over two winIDEA instances. This still does not really allow efficient timing analysis from end to end, like automatic timing metrics calculation, like min-max times, and all these goodies of a real timing analysis tool. So obviously the question is, how can we combine those two traces? As possible solutions for that, I want to present two approaches here. The approach I want to describe first basically uses a third-party timing analysis tool for the actual event chain analysis. So how do we get the traces into these tools? We use a trace exchange format called BTF, which stands for best trace format. So yes, no kidding, this is really what it stands for. So this BTF format is well understood by all major timing analysis tools like Vector, TA tool suite, the Incron tool suite, and also the Luxoft LuxTrace. And the easiest way for combining these traces is to export each trace separately in a BTF file, then merge them and import the resulting merge BTF into the timing tool. I will demonstrate this later on using the Vector TA tool suite. The other approach is entirely based on iSystem tools. Unfortunately, we do not have the possibility yet to merge two traces and analyze them in one of the winIDEA instances. Therefore, we need to work around this a little bit and use some tricks. The idea is to synchronize events of one winIDEA instance to the other instance. We can do this by having, for example, the master to signal an event by toggling an output pin. Then we measure this master ECU pin toggling by our IDEO box connected to the BlueBox of the slave ECU. This allows us to combine a master ECU event with the traces of the slave ECU. And finally, we utilize our profiler inspectors for analyzing the complete chain of events. I will also demonstrate this approach. For demonstrating the first approach, I will use, as I said, the Vector TA tool suite, actually the TA inspection tool of the tool suite. The resulting event chain will look like this as shown here in the screenshot. So how do we get there? This is basically the workflow concerning the iSystem tools. We, of course, start with synchronized trace recording on both ECUs. And from the individual traces, we export a BTF file. Another simple trick is that we merge those two BTFs. Each line in the BTF represents an event, such as a task start, maybe a runnable terminate, or maybe also a CAN frame start. And each of these events has its own timestamp value in nanoseconds. This here, the first entry here. The merging simply reads in all the events from both BTFs, sort them according to the timestamp, and writes them into the output file. And what we also do is we add a prefix to the so-called source name of each event. So for all events in the master, we add M prefix. And by doing this, the timing analysis tool does not necessarily be able to handle a real multi-ECU timing analysis. This is basically handled like a multi-core analysis with just more cores. And yes, the merge BTF is then simply imported in the tool suite, and this is what I'm going to show you now. Here in winIDEA, we already have a trace recording, so all what needs to be done here is the export of the BTF on both sides. I will limit the scope of the export to the time range between 2 and 4 seconds, so we basically export everything between the blue and the yellow cursor. And we can do this by simply clicking this export icon here, select BTF and do the export. And the same here on the slave. On the command line, I'm calling the script which merges the two BTFs. The result is this file merged with prefix .btf. Okay, now I can switch to the TI tool suite and import the BTF into an existing timing model. Here we have the TA inspection tool of the Vector TA tool suite. I already have a timing model in the workspace, so I'm basically just adding a new trace import to it. Part of this timing model is also a description of our event chain. This is stored here in this TAM file. Now I'm importing the new BTF. So we already see the trace result here in the Gantt chart. But we still need to do the actual event chain analysis. And for this, we need to re-evaluate the new trace. And make also the event chain visible in the Gantt chart. And here we go. Here we have our event chain in the Gantt chart. Starting from the main function tx on the master to the transmission of the master request frame, the can receive interrupts on the slave, which activates the RT event task and calls the modify echo runnable, and also the basic software function com_send signal for transmission of the can acknowledge frame on the bus. And down here we have the metrics calculated for all the dedicated event chains with min, max, average time for the entire chain and also for sections of the event chain. Like here, for instance, this EC1 section, which is actually a delay between the basics of the main function until the can frame gets transmitted on the bus with its minimum, maximum, and average time. Okay, so this would be the approach for using a third-party tool. The other approach is, as I said, based on iSystem tools only. And the goal here is to have the entire event chain, including the start point on the master ECU, visible in one winIDEA analyzer view. This will then allow us to evaluate the event chain with a specific analyzer feature which is called inspector. So finally, what we get is an event chain visualization like shown here in the screenshot with all the stages of the event chain. So let me first explain the idea of this concept. We have our two ECUs with synchronized trace tools attached and individual trace recordings. What we want is to synchronize the start point of the event chain, this basic software function main function tx, into the profiler timeline of the slave's ECU. And we can do this by toggling a pin of the master AURIX device when we enter this function. Now the nice thing about AURIX is that we do not need to add any instrumentation code for this pin toggling. The on-chip trace logic of the AURIX, the so-called MCDS, allows to specify an address, and when the instruction located at this address gets executed, it automatically asserts a pulse on an MCDS trigger output. In our case, we use this TG4 output pin. And obviously, here we configure the MCDS in a way to assert the TG4 pin when we enter the main function TX. This signal here basically represents this MCDS trigger event. And now we trace this TG4 pin with our IDEO box, which is connected to the blue box of the slave. This IDEO trace is now synchronized into the trace of the slave ECU. So we see this master trigger signal here in the profiler timeline of the slave. And of course, I will also demonstrate this concept in winIDEA. We still have here the exact same workspace as we used previously for the BTF export. So on the left side, we have the master ECU, and on the right, the slave. And I have already recorded a synchronized trace. So first, let's look at the master. Here, the interesting thing is the trigger signal asserted on entry into this main function TX. And as I said, we configure the MCDS to automatically assert a pulse on the TG4 when we enter this function. And so in the profiler, I've added this object here, this MCDS TG4, which indicates when this trigger is sent out with the TG4 pin. Basically here, we more or less enter this function. So this TG4 signal is now measured by the IDEO box connected here to the slave. Here we have this data IO, digital IO trigger master object in the aux view, which is what's measured by the IDEO box. And I have replicated this exact same signal here in the data view along with the task runnables and some other inspectors. So now we have the entire event chain in one profiler timeline. And by the way, here we can see that the master and the slave trace are actually synchronized, because now we can actually look at the same event on both ECUs. So the exact point in time when the master enters this main TX function, we see the IDEO master trigger event also here in the slave trace. So the location of the black cursor in both the master and the slave timeline is pretty much the same, just a difference of a few hundred nanoseconds. Okay, let's look at our event chain. So here we have the start point, basically the execution of this main function in the master, the CAN frames on the bus, and also the ISRs, tasks, and runnables on the slave. And now that we have this, we can further analyze our event chain by means of our profiler inspectors. This is what I've done here. So just quickly, what is an inspector? An inspector is an advanced feature of the profiler. It allows to do a post-analysis of the profiler result. Basically, all these objects here, these are results of the native profiler analysis, like the runnables and the OS tasks. Now with an inspector, I can run a further analysis of these profiler objects and basically create new objects, these inspector objects, indicated by this type of symbol. And I'm using an inspector for creating these objects here, representing all the stages in our event chain. So the inspectors They inspect the profile objects like the master trigger from the DIO, the ISRs, the tasks, runnables, and can frames. And whenever it detects certain events, basically when a new stage of our event chain is entered, the inspector goes in the next state of its internal state machine. Let me show you how this inspector for this event chain looks like. So this is the icon for opening the inspectors, and we're looking into this event chain state machine inspector. Here in the events section, we can specify all events which will later be used to control this inspector state machine. So here we have events like master trigger, can frame master request start and end, can ISR entered, and so forth. And here we use these events to control the state machine. Like here, for example, starting from the initial idle state, we can enter the state S1, master basic software function TX, when we detect this the trigger signal from the master. Or maybe here, we change from state S5 com send signal to S6 can frame slave acknowledge active when we detect, while we are in state 5, that the slave acknowledge frame is actually sent on the bus. And all these states are displayed in the profile timeline, basically visualizing our event chain. And since I have the event chain now in the profiler timeline, I can also apply all the profile analysis features on them, like searching for min, max time occurrences. And for measuring the total latency of the entire event chain, I created actually another inspector, this one here, which measures the time from start of state S1 until the end of state S6. And of course, the profiler also calculates the corresponding statistics for this EC total latency object. And since there may be some incomplete event chains at the beginning and at the end of the trace, I'm using here another handy feature of the profiler. I simply limit the statistic analysis to a certain time interval instead of the entire trace recording. I can do this by simply setting the blue and the yellow cursor and create an interval statistics view. So here we have the event chain statistics for defined time range with its min, max, average values. And you can also let the profiler point you to the event chain instance with, for example, the maximum latency. So let's zoom into this particular event chain which shows the maximum latency. You see that the latency makes quite a big step from this 830 to 1042 microseconds. So let's see what the root cause might be for this increased latency. So let's look at the transmissions on the bus. We see, for example, that we have a frame 200, which is transmitted, still needs to be transmitted when then we have a frame 105, which is apparently higher priority than our master request frame. And yeah, that's probably the root cause why our master request frame is quite some delay, and this obviously causes also the entire event chain to have quite some delay. Okay, yeah, this is what I wanted to show and explain to you. I hope you're now deeply impressed. No, seriously, I hope you found this useful, and maybe you think about this webinar when you're confronted with some event chain communication latency or maybe synchronicity timing requirements. in one of your next projects and you don't really know how to measure them. We might have a solution for you. Okay, and now we're open for some questions.
Thank you, Armin, for your demonstration. As you said, let's continue with the Q&A session. The first one is, how accurate is the time synchronization between the two ECUs?
Yeah, this depends actually on whether timestamping is done internally or done with off-chip timestamping, as I explained in the webinar. For external timestamping, for example, the synchronization accuracy between the blue boxes is basically the accuracy of the timestamping count of the blue boxes itself, and they're synchronized down to one timestamp tick number. So basically, two timestamps really run exactly the same at the same level. But I have to admit, there is still since there is still some buffering going on within the chip. The two traces may not be 100% like down to each nanosecond synchronized, but this is an effect you also see. This kind of tracing inaccuracies is an effect you also see when you trace these kind of targets individually. So this is nothing with has nothing to do with the synchronization concept itself. The other option is basically that you use processes which use on-chip timestamping, that what we've done here with the AURIX device. There, the achievable accuracy depends a bit on the individual processor, and I can't go into too much details now, but so far on the SoCs we support at the moment, we can definitely go down to an accuracy level below 1 microseconds for the synchronization.
Thank you, Armin. The second one is, you mentioned once also the IC5000. Does the synchronized trace also work with an IC5000?
Yeah, this was probably an error on my side. No, actually, it only works with an IC5700, not with the 5000. This is because only the 5700 offers this FNet connectivity to add the add-on modules, and only the 5700 can be equipped with the synchronization hub, which is really necessary for this trace synchronization of two blue boxes via this F bridge that I explained previously. So this feature is only available with the IC5700.
Thank you, Armin, again. How many ECUs can be traced in a network is another question.
Yeah, currently we have the infrastructure to trace two ECUs in parallel through this F bridge directly connected between two IC5700s. So currently limited to two. We have, however, another piece of equipment currently in development, which allows them to extend this to, I think, 6 IC5700. So this, we don't have this product yet, but this is something we have in development at the moment.
The next one is about a CAN bus. Is the tracing of the CAN bus needed for the synchronization between the two ECUs, or does it also work without CAN?
The synchronized trace of the two ECUs is totally independent of the CAN bus tracing. In this demo, I just used this for complete description of this event chain that to demonstrate we can also include the bus tracing, the bus behavior into the overall event chain analysis. But for the synchronization itself, it's not needed at all. So.
Thanks, Armin. And another one is on CAN and ADIO trace. You mentioned that also CAN trace and ADIO trace can be used to generate a trace trigger. How would that work?
Oh, yeah, well, is a bit tricky. When you hook up those two blue boxes via this FNet and FBridge connections, then what you do is you can form kind of a trigger signal matrix, which then can be configured by the user as its individual needs. And what you could do, for example, you could configure the CAN LIN box for the CAN tracing to, for example, assert a trigger when it detects a frame with ID 110, for example, on the bus. And then within winIDEA, you configure the whole system in a way that this event generated by this CAN box can be used as a common trace trigger, for example, or it can be used to stop the CPUs, or can be used for various different purposes. So same goes basically for the IDEO box. There you can also specify, for example, that when it detects a certain digital signal goes low for at least maybe 10 milliseconds or something like that, then this signal could be used to stop both ECUs synchronously. So you can create a very flexible scheme of event detection and action triggering within the overall system.
Thank you, Armin, for sharing your knowledge with us. We're coming to an end for this episode. All questions which were not answered now will be answered by email shortly. And before you leave, I would like to give you some additional information. Do not forget to download the presentation in the handout tab of the menu bar. Check out our free online trace tutorial, our various application notes, and our YouTube channel where this webinar will be hosted, and others are already available. And if you want to, feel free to register for our newsletter to get interesting updates automatically. If questions come to your mind later, feel free to send an email to webinar@isystem.com or contact your iSystem contact person. Thank you for attending, and please fill in the feedback form after leaving. Merry Christmas, Happy New Year, bye, and take care.